Hello everyone, this is Dr. Prashanthi, Assistant Professor, Department of Chemistry, Government Degree College for Women, Karimnagar. In today's session, I am going to discuss about the part 2 of amines. In the part 1 of amines lecture, I have discussed about the introduction, some of the biological and industrial uses of amines, about the structure and bonding, and about the classification of amines into primary, secondary, tertiary and quaternary amines, and the nomenclature of amines, both the common system and IUPAC system. And we have discussed about the preparations of amines, and in the preparations also we have seen ammonolysis of alkyl halides, Schmidt reaction, reduction of amides, Gabriel synthesis, and the most important Hoffman bromamide reaction. And then lastly we have discussed about the physical properties of amines also. And in today's session I am going to discuss about the basic nature of amines, basic character of amines, and the comparison between the alkyl amines and aryl amines regarding the basic nature and uses of amines as phase transfer catalysts, and some chemical properties of the amines. Then coming to the basic nature of amines, the basic nature is due to the presence of unshared electron pair on nitrogen atom. See, we all of us know that one unshared electron pair is present on the nitrogen atom of amines. Therefore, this is readily available for donation. Therefore, all the amines shows the basic nature. Due to this presence of unshared electron pair on nitrogen, it can accept protons from acids, which determines the relative basic strength of the amines. This availability of a lone pair of electrons for coordination with the proton determines the relative basic strength. And we all of us know that methyl or alkyl groups are attached to the methyl, or any other alkyl groups are attached to the amines. See, we have seen in the first part that if one alkyl group is present on the nitrogen atom, it is primary amine. If two alkyl groups are present, it is secondary amine. If three alkyl groups are present, it is tertiary amine. And we know that alkyl groups are positive inductive effect groups. So, nitrogen atoms have alkyl groups, it is bonded to alkyl groups. Therefore, the inductive effect of alkyl groups, because of this effect, the nitrogen atom becomes strongly electronegative. Due to this, the lone pair of electrons on nitrogen atoms is more readily available than in ammonia. Therefore, amines are considered as stronger bases than ammonia because of the presence of the alkyl groups, which are positive inductive effect groups. Okay, these alkyl groups increases the basicity of amines. Hence, as the methyl groups increases, the basic strength also increases. So, the basicity of amines should increase with the increase in the number of the alkyl groups. So, according to this point, because of the inductive effect of alkyl groups on the nitrogen atom, the acid basic strength is increasing. So, according to this point, the basic strength or the basicity of different amines should be in the following order. See, we have primary, secondary and tertiary amines. Okay, according to this effect, according to this electron releasing factor by the alkyl groups, tertiary amines should be more basic in nature than secondary than primary amines. But the actual order of basic strength is secondary is more basic, and secondary amine is more basic than primary than tertiary, which are further more basic than ammonia. The actual order is found to be this, because as the alkyl groups increases around the nitrogen atom, they cause crowding, and the lone pair electrons that are present on the nitrogen atom in the tertiary amine will be unavailable for donation. See, as the number of here in primary amines we have only one alkyl group or methyl group. Here we have given the example of a methylamine. This is primary, this is secondary, and this is tertiary amine. Here we have only one methyl group, here we have two methyl groups, and here we have three methyl groups. But according to the electron releasing factor, primary trimethylamine or tertiary amine should be more basic than secondary than primary. But because of the crowding of these alkyl groups around the nitrogen atom, these alkyl groups are making some steric hindrance. They are creating some steric hindrance in the molecule, and therefore the lone pair of electrons present on the nitrogen atom will be unavailable for donation. So because of this, the basic strength of the tertiary amines is decreasing. Then in aqueous solutions, the basic strength not only depends upon the electron releasing factor, but also depends upon the steric effect and hydration effect also. Let us see what are they. Steric effect. With the nature of the alkyl groups, the basic nature of various amines also varies. We have seen that secondary amines are more basic than primary than tertiary. So if the alkyl group is a methyl group, if alkyl group is methyl group, dialkylamine is more basic than dimethylamine is more basic than methylamine than trimethylamine. But if the alkyl group is a ethyl group, then the order is changing. That is, secondary amine is more basic than tertiary amine, which in turn is more basic than primary amine. So in aqueous solution, depending upon the nature of the alkyl group, also the basic strength is changing. Next, coming to the hydration effect. What is hydration effect? It refers to the stabilization of the protonated amine by water molecules. See, here the water molecules form hydrogen bonding with the protonated amine and releases energy called as hydration energy. Greater the extent of hydrogen bonding in protonated amines, more will be its stabilization. Therefore, primary amine is more stable more stable and is more basic than secondary amine, which in turn is more basic than the tertiary amine, because in primary amine we have two hydrogen atoms. Therefore, there is a possibility of two hydrogen bonds in primary amine with the water molecules. Therefore, greater will be the basicity also, and basicity of the primary amines. And along with these two hydrogen atoms, the lone pair of electrons present on the nitrogen atom are also forming hydrogen bondings. Therefore, there is a possibility of three hydrogen bondings in primary amines. And when coming to secondary amines, there is one hydrogen atom and the lone pair of electrons on nitrogen also form hydrogen bonds. Therefore, there is a possibility of two hydrogen atoms. And coming to tertiary amines, here it does not have any hydrogen atoms. Even though it has no hydrogen atoms, that is directly hydrogen atom is not directly attached to it, but it can also form hydrogen bonding by using its lone pair of electrons. That is, therefore, the lone pair of electrons in this way they can form hydrogen bondings with the water molecules. So, according to this concept, primary amines should be more basic than secondary than tertiary, because primary is having two hydrogen atoms, secondary is having one hydrogen atom, and tertiary amines does not have any hydrogen atoms. So, tertiary amine is least stable. Actually, it has maximum plus inductive effect. That is, three alkyl groups are present, and the alkyl groups are electron releasing groups. So, electron releasing groups, they release more electrons onto the nitrogen atom, and the nitrogen atom has rich electron density on it which are available for donation. Even though it is least stable, it has maximum plus inductive effect. And primary amines are most stable, but they have a minimum positive inductive effect. So in practice, these two opposing forces factors balance each other in the case of secondary amine, and finally which makes a secondary amine more basic than primary amines. And therefore, by concluding or by taking into consideration of all these factors, that is um, uh, electron releasing factor, steric effects and hydration effects, by considering all these factors, finally it was concluded that secondary amines are more basic than tertiary primary than primary. So in this way, the basic strength of amines is explained by taking into consideration of electron releasing factors, steric effects and hydration effects. Next, finally it is based on the combination of electron releasing factors, steric effects and hydration effects. The basic strength of aliphatic amines is as follows. Secondary amines are more basic than tertiary amines than primary amines. Then coming to the comparison between the aryl amines and alkyl amines. See, aryl amines, aniline, see, aryl amines means NH2 group is bonded to one, NH2 group is bonded to one phenyl ring. That is, this aniline is the best example and important example. And when we come to the basic strength of aryl amines first, aniline is less basic than ammonia. See, ammonia is also having lone pair of electrons on nitrogen atom, and aniline is also having lone pair of electrons on the nitrogen atom. But even though aniline is found to be less basic than ammonia, because the phenyl group is a negative inductive effect group, that is, it withdraws electrons towards itself. In the previous heading, we have seen that alkyl groups are positive inductive effect groups, that is, they are electron releasing groups. But here phenyl groups are negative inductive effect groups, that is, they withdraw electrons. Therefore, the electrons present on nitrogen atom are less available for protonation. So, they are not readily available for protonation. Electron withdrawing groups decreases electron density on nitrogen atom, which in turn decreases the basicity. Therefore, when aniline and ammonia are compared, aniline is less basic than ammonia. Next, coming to the comparison between aryl amines and alkyl amines. Aryl amines are weaker bases than alkyl amines. See, we know alkyl amines are positive inductive effect groups, electron releasing groups, and aryl amines are negative inductive and electron withdrawing groups. Alkyl groups increases the basicity of aromatic amines. N-alkyl anilines are stronger bases than aniline. See these are alkyl amines. This is the general formula for alkyl amines. Alkyl groups are electron releasing groups, so they release electrons to the amino group. And here this is aryl amine. Aryl group is electron withdrawing group, so it withdraws electrons from the amine group. See here, so it is withdrawing electrons, therefore here the basicity decreases. Here in the case of alkyl amines, the basicity increases. And I'll give you some examples. Aryl amines are weaker bases than alkyl amines. See, aryl amines are weaker bases than alkyl amines. We know in alkyl amines, electron releasing groups increases the electron density on nitrogen atom, and the ability of amine for protonation also increases. In aryl amines, the electron withdrawing groups are decreasing the electron density on the nitrogen atom, and is therefore it is less available for protonation. And the important point is in alkyl amines, the electrons present on the nitrogen atom are localized. They are localized and readily available for protonation. But in aryl amines, that is for example in the case of aniline, in aryl amines, this is aniline, the lone pair of electrons present on the nitrogen are delocalized. Okay, they are not present on the nitrogen, but instead they are delocalized into the benzene ring by resonance. Therefore, they are less available for protonation. That is, they are in conjugation with the benzene ring in this way. The electrons present on the nitrogen atom are participating in resonance with the benzene ring. Therefore, the electrons are moved onto this orthocarbon atom, and here this carbon gets more electron density. Therefore, again the electron density is moved to the para position in this way. So, this gets minus charge here, that is a more electron density is present now at this carbon atom. And these electrons are moved to this ortho position. This carbon atom is now having more electron density on it, and again these electrons are moved back to the nitrogen atom NH2. So, these are the resonance structures of aniline, that is electrons involving in delocalization with the benzene ring. So, as they are involving in delocalization with the benzene ring, these electrons are not readily available for donation. Therefore, aryl amines are less basic than alkyl amines. Aryl amines are weaker bases than alkyl amines. Then coming to the aryl alkyl amines. What are aryl alkyl amines? That is, aryl group will be present. Aryl group is bonded to the alkyl group, which is further bonded to the amine group. That is, here in aryl alkyl amines, the amine group is not directly bonded to the aryl group or aryl carbon atom. Amine group is bonded to the alkyl group that is present in the as the side chain in the aryl group. Okay, that is, see, this is don't get confused with all these terms. See, this is alkyl amine. Alkyl group is bonded to the amine functional group. If phenyl group is bonded to the amine group or amine functional group, they are called as aryl amines. Alkyl group, alkyl amines. If amine functional group is bonded to the alkyl group that is present as a side chain in the benzene ring, then it is called as aryl alkyl amine. So, aryl group is present, alkyl group is present, and amine functional group is present. So, aryl alkyl amine. So, if we come to these amines, the aryl alkyl amines are stronger bases than aryl amines, but weaker than alkyl amines. See here, the overall order is alkyl amines are more basic than aryl alkyl amines, which in turn are more basic than aryl amines, because in alkyl amines R is the positive inductive effect group. So, it is electron releasing group. Okay. And in aryl alkyl amines, the nitrogen atom is having lone pair of electrons that is not in conjugation with the double bond of the benzene ring, because this is not directly attached to the aryl group. This is indirectly attached, or this is attached to the alkyl group which is a substitute of aryl ring. Therefore, there will not be any delocalization. Therefore, this is basic than aryl amines. In aryl amines, NH2 group is directly bonded to the benzene ring. Therefore, these electrons will be in delocalization with the pi electrons of benzene ring. Therefore, these are not available readily for protonation. Therefore, aryl amines are less basic. So, the order is alkyl amines. Alkyl amines are more basic than aryl alkyl amines, which are more basic than aryl amines. In this way, and we can I have to tell you one more thing here, that is we are talking about aryl amines. Okay, suppose the substituents that are present on the ring, or the substituents that are present on the nitrogen atom also affect the basic strength. That is, for example, if the two hydrogen atoms present on the nitrogen, two hydrogen atoms present in the aniline present on the nitrogen atom of aniline, if they are replaced by, suppose in two hydrogen atoms, if one hydrogen atom is replaced by one methyl group, and if we take another example, in two hydrogen atom, if two hydrogen atoms are replaced by two methyl groups, okay, what will be the basicity order? See, this is aryl amine. These nitrogens are in delocalization with the benzene ring, so less basic, that we know, we have seen just now. If this one of the hydrogen atom is replaced by one methyl group is an electron releasing group, therefore it increases the electron density on the nitrogen atom. Okay, therefore increases the basic character. Suppose if the two hydrogen atoms are replaced by two methyl groups, then both the alkyl groups are electron releasing, and therefore they increase more electron density on the nitrogen atom. Therefore, when compared, if we compare all these three examples, this dimethyl aniline is more basic than monomethyl aniline or N-methyl aniline, which in turn is more basic than our aniline. That means if electron releasing groups are present on the nitrogen atom of aniline, they increase the basicity of or they increase the basic character of the amine. Okay, understand. If electron releasing groups are present on the nitrogen atom of aniline, they increase the basic strength of the amines. Then suppose if electron withdrawing groups are present, then what will happen? Let us see. See, this is our NH2, this is our aniline. Okay, suppose if an electron releasing electron withdrawing group like a phenyl ring is bonded, is replaced here, then what will happen? See, this is electron withdrawing group, therefore it withdraws electrons towards itself. Electrons are withdrawn by the phenyl ring, therefore it decreases the basicity. Suppose if the two hydrogen atoms of amine functional group are replaced by two phenyl groups, then the withdrawing will be more, which further decreases the basic strength. So, in these cases aniline is more basic than this diphenylamine, which in turn is more basic than this triphenyl aniline. Okay, that means aniline or aryl amines are generally less basic in nature. If electron releasing groups are present on the nitrogen atom of aryl amines, they increase the basicity of aryl amines. If electron withdrawing groups are present on the nitrogen atom of amines, aryl amines, they decrease the basic character of amines. Okay, in this way all the amines shows their basic nature, and finally alkyl amines are found to be more basic than aryl alkyl amines, which are more basic than aryl amines. See, this basicity of amines and comparison between ammonia and alkyl amines, between ammonia and aryl amines, between alkyl amines and aryl amines, between aryl amines and aryl alkyl amines, all these points are very important, and this heading basicity of amines or a basic strength of amines is a very important question, very important essay type of question for the final examinations. Next, amine salts as a phase transfer catalysts. What are phase transfer catalysts? Phase transfer catalyst is a catalyst which facilitates the migration of a reactant from one phase into another phase where the reaction occurs. See, normally in organic substitution reactions, especially nucleophilic substitution reactions, the nucleophile is soluble in water, but the organic reactant is not soluble in water, it is soluble in organic layer. Therefore, the two reactants will be in different liquid phases, which makes the nucleophilic substitution reaction very difficult one. Therefore, phase transfer catalyst is added to this reaction in order to perform the reaction well. That is, phase transfer catalyst is a substance which dissolves in both the layers, that is in both the organic layer and the aqueous layer. It reacts with the nucleophile and transfers it into the organic layer. Therefore, this catalyst is used for solubilizing the salts into the organic phase. And here the fourth type of amines, that is quaternary amine salts, are mostly used as phase transfer catalysts. So, tetraalkyl ammonium salts are used as PTCs. Suppose if you take the example as shown in the slide, this is butyl bromide. 1, 2, 3, 4 carbon atoms are present that are bonded to one bromide ion. This is a butyl bromide. This, on reaction with the sodium cyanide, what happens? Actually, the two reactants are immiscible. These two reactants are they do not mix with each other and the reaction does not occur actually, but these two reactants can be made to react with each other if a phase transfer catalyst is added to the reaction mixture. And so to perform this reaction, phase transfer catalyst is added, and here mostly tetraalkyl ammonium salts are added. These salts acts as mediator between the immiscible solvents. So what happens here is actually these phase transfer catalyst passes from aqueous layer into the organic layer. Okay, and while passing into the organic layer, it carries a counter ion with it. So mostly the counter ion will be, here we have taken the example as cyanide ion, therefore mostly the counter ion will be the cyanide ion. Therefore, and also here in the solution more cyanide ions are present, therefore mostly cyanide ion will be taken by the phase transfer catalyst to the organic layer, and after entering into the organic layer, this cyanide ion reacts with the alkyl halide. See what happens is in the aqueous solution. See, suppose if we have a reaction mixture. Okay, this is a organic layer having butyl bromide, and this is a aqueous layer having sodium cyanide. See, both are immiscible, they do not mix with each other. So in order to perform the reaction between these two reactants, a phase transfer catalyst is used. The PTC used in this reaction is tetraethyl ammonium chloride. See, here we have written here tetraethyl ammonium chloride is used as PTC in this above reaction. Okay, so tetraethyl ammonium chloride is added to the reaction mixture. This tetraethyl ammonium chloride and both tetraethyl ammonium chloride and our cyanide ions are present in the aqueous layer, in this aqueous layer. So what happens here is the chloride ions are released into the solution and the cyanide ions are taken up by the tetraethyl ammonium chloride. So now what happens here, see here in the solution, tetraethyl ammonium chloride and cyanide ions are present in the aqueous solution. So in the aqueous solution the exchange of ions takes place and now we have tetraethyl ammonium cyanide. Tetraethyl ammonium cyanide and chloride ions are left behind. And now this tetraethyl ammonium cyanide is now able to pass into the organic layer from aqueous layer. So now this passes into the organic layer which is having butyl bromide. Okay, so now it becomes easy for the cyanide ions to move into the organic phase with the help of tetraethyl ammonium salt. And in the organic layer, tetraethyl ammonium cyanide reacts with the butyl bromide. See, these PTC cyanide ions are coming into the organic layer with the help of our PTC. There the reaction occurs between the two reactants. So now the exchange of ions takes place here in the organic layer. So the bromide ion of this butyl bromide is now replaced by the cyanide group, cyanide ion of tetraethyl ammonium cyanide, and bromide ion is taken up by the tetraethyl ammonium salt. Okay, in this way the cyanide ions which are not able to pass into the organic layer are made to pass into the organic layer with the help of tetraethyl ammonium chloride. In this way the two reactants react with each other and forms this butyl cyanide is formed. And lastly we are getting a tetraalkyl or tetraethyl ammonium bromide. This again enters into the here along with the butyl cyanide. We are also getting tetraethyl ammonium bromide, and this tetraethyl ammonium bromide again enters into the aqueous phase, and again the same process is repeated. In this way the reactions which are immiscible can be made possible with the help of the these tetraalkyl ammonium salts. In this way these are used. This is also an important question for 4 marks. Next, coming to the chemical properties of amines. See, what are the chemical properties the amines undergo? One is alkylation. So primary amines reacts with alkyl halides and forms secondary, tertiary amines and quaternary ammonium salts. See, primary amines RNH2 react with alkyl halides. So one of the hydrogen is replaced by one alkyl group, and this hydrogen is left as HX. So R2N, this is nitrogen is bonded to two alkyl groups, therefore it is a secondary amine. And this secondary amine again on reaction with the alkyl halides, they gives rise to tertiary amines. That is, this hydrogen is lost as HX and this R is bonded to the nitrogen atom, giving rise to tertiary amine. And also tertiary amines on reaction with again one molecule of alkyl halide, we get quaternary ammonium salt. Here we have taken one example, that is a methylamine on reaction with methyl iodide. Here hydrogen atom is lost as Hi, and this methyl group is bonded to the nitrogen atom, so that we are getting secondary, that is CH3 taken 2 times NH. Secondary amine, that is dimethylamine, is obtained, which again reacts with the methyl iodide and forms trimethyl amine, which is a tertiary amine. Again this tertiary amine on reaction with the methyl iodide is giving the quaternary salt, that is a tetramethyl ammonium iodide. In this way the amines undergoes alkylation. Next, acylation. Primary and secondary amines reacts with the acid chlorides or acid anhydride to form N-acyl amides. This reaction is nucleophilic acylation at the carbonyl group. Here the nucleophilic substitution occurs. And high electronegativity of chlorine atom reduces the electron density at the carbonyl carbon. This makes the nucleophilic substitution very easier. Here H, this is an example for primary amines on reaction with the acyl chlorides. Here H from NH2 one hydrogen is lost as HCl, and in the place of this hydrogen this acyl group goes and attacks and forms RC double bond O NH2R C double bond O NHR is obtained. And we have one more example here, benzylamine. This on acylation or when treated with acetyl chloride, CH3COCl, this is acetyl chloride. Here hydrogen is lost as HCl, and in the place of this hydrogen this acyl group goes and attacks. Therefore we get a benzene group, phenyl CH2 NH bonded to COCH3. And not only with the acetyl chlorides but also with acetic anhydrides, they are giving rise to the the acetylation is occurring. And here we have taken the example of secondary amine, that is diethylamine on reaction with acetic anhydride is giving N-dimethyl acetamide. Here the H is lost here, and acetyl group is bonded to the nitrogen atom. Here COCH3 is bonded here. Next, carbyl amine reaction. Primary amines in the presence of alkalis, they react with the chloroform and gives carbyl amines or isocyanates. This reaction is called as carbyl amine reaction. Isocyanates are foul smelling toxic substances. This reaction is useful for the identification of primary amines. Primary amines when react with chloroform in the presence of any alkali gives isocyanates, that is N triple bond C bond is present in these compounds, that is they are called as isonitriles or isocyanates, which are very foul smelling toxic substances. And this reaction is given by only primary amines, therefore this is used for the identification of primary amines from secondary and tertiary amines. This is another example for a carbyl amine reaction. This is aniline. Aniline on carbyl amine reaction is giving phenyl isocyanate. Next, reaction with nitrous acid. Primary, secondary and tertiary amines, they react differently with the nitrous acid. Primary amines, they give alcohols with the nitrous acid. Primary amines, they give alcohol with the nitrous acid, but methylamine, see methylamine is a primary amine but it does not give alcohol with nitrous acid. Instead it is giving, methylamine is giving dimethyl ether with nitrous acid. And this is one another example, ethylamine on reaction with the nitrous acid, it is giving ethyl alcohol. It is giving ethyl alcohol. And coming to secondary amines, they react with nitrous acid and forms N-nitrosoamines. N, see, N-nitrosoamines which are soluble ether but insoluble in water. See, these are yellow liquids which are insoluble in water. See, this is a general equation for the reaction of secondary amine with the nitrous acid. See here H2O is lost and NO is bonded to the nitrogen atom, and so nitrosoamine is formed in this way. And this N-nitrosoamine, this when treated with the phenol, okay, when treated with phenol in the presence of concentrated H2SO4, it gives a deep blue color solution. Okay, deep blue color is obtained. This is and this type of or this test is used for the identification of secondary amines, for qualitative test for secondary amine, used as qualitative test for secondary amine. See, in the previous reaction we have seen that carbyl amine test is given by only primary amines, therefore it is used to identify primary amines from the other amines. And this particular reaction with the reaction of secondary amines with the nitrous acid is used as a qualitative test for the secondary amines, because the nitrosoamines which are obtained by the reaction of secondary amines with the nitrous acid on reaction with the phenol and concentrated H2SO4 are giving blue color solutions, and this type or this reaction is called as Lieberman nitroso reaction. Lieberman nitroso reaction, which is used for secondary amines. And these secondary nitrosoamines are found to be poisonous and even carcinogenic in nature. And coming to the tertiary amines, they react with the nitrous acid and gives water soluble salts. Okay, the tertiary amines, they are giving salts which are soluble in water. So in this way HNO2 test or a nitrous acid test is used to distinguish between primary, secondary and tertiary. If you observe, the secondary amines are giving nitrosoamines, but they are soluble in ether. But when coming to tertiary amines, they are giving salts which are soluble in water. So this is an important test for distinguishing between primary, secondary and tertiary amines. Next. Next is Hinsberg's separation of amines. See, till now we are talking about the primary amines, secondary amines and tertiary amines. Then now we will discuss about the separation of these amines. Suppose if we have a mixture of all these amines, how these amines will be separated. Okay, first of all, the mixture of all these the primary, secondary, tertiary amines and quaternary salt can be separated by the distillation. Okay, first the mixture is distilled with the potassium hydroxide solution, where the mixture of primary, secondary and tertiary amines distills over, and the quaternary salt does not react with the potassium hydroxide, therefore it is left behind. So in this way, first by the distillation, primary, secondary and tertiary amines are separated from quaternary salts. Okay, then now the mixture of primary, secondary and tertiary amines are separated by Hinsberg method. And what is this Hinsberg separation? Let us see. See, in this Hinsberg reaction, benzene sulfonyl chloride is used as reagent. Benzene sulfonyl chloride, that is benzene sulfonyl chloride. This is used as the reagent, therefore it is called as the Hinsberg reagent. In this the primary, secondary amines in ether solution reacts with the benzene sulfonyl chloride and forms and forms sulfonamides. See here, tertiary amines, as they do not possess hydrogen atoms on the nitrogen atom of their amine functional group, they do not react with the benzene sulfonyl chloride. So, first of all, the mixture of all these three amines is treated with Hinsberg reagent. Primary and secondary amines react with the benzene sulfonyl chloride because they are having hydrogen atoms on the nitrogen of nitrogen functional group. But primary amines, they do not, because they do not have any hydrogens, therefore they can be separated here by again distillation. Therefore tertiary can be separated by distillation. Okay. Then what happens when primary and secondary amines reacts with the benzene sulfonyl chloride? So when they react with benzene sulfonyl chloride and treated with sodium hydroxide and ether, primary amines react with, see, these are primary amines having two hydrogen atoms. Primary amines react with the benzene sulfonyl chloride, HCl is lost. Okay, N-alkyl sulfonamides are obtained. N-alkyl and alkyl substituted nitrogen, N-alkyl sulfonamides are obtained. This N-alkyl sulfonamide, on treating with any alkali, suppose for example potassium hydroxide, okay, on treating with KOH, it forms a potassium salt of N-alkyl sulfonamide. Potassium salt of sulfonamide is obtained, which is soluble in water. This is water soluble. This is soluble in water. Okay. Coming to the secondary amines also react with the benzene sulfonyl chloride because they are also having one hydrogen atom. Therefore, they react with benzene sulfonyl chloride and they form N-N dialkyl, because two alkyl groups are substituted on the nitrogen atom. So, N-N dialkyl sulfonamide is obtained. Okay, but this does not react with the KOH. Because see here, here primary amines are having two hydrogen atoms. So one hydrogen atom reacts with the Cl ion of benzene sulfonyl chloride and the other hydrogen atom, it reacts with the it reacts with the alkali, and therefore it is giving rise to the potassium salt of sulfonamide. Okay, but in case of secondary amines, only NN dialkyl sulfonamides are obtained, but it does not have any hydrogen atoms, therefore it does not react with the potassium hydroxide, and it is ether soluble. It is soluble in ether. By separating the aqueous layer and ether layer, primary and secondary amines can be separated. They can be regenerated. And we have seen that tertiary amines does not react with the Hinsberg reagent. Okay. So in this way, all the three amines and all the four amines are separated using this technique. First of all, the mixture of all the four types of amines are first separated by distillation, where quaternary amines are separated during this distillation. Primary, secondary, tertiary amines remain in the solution, and these three amines can be separated by using Hinsberg method. By using Hinsberg separation, for this Hinsberg reagent, benzene sulfonyl chloride is used as a reagent with which primary amines reacts, okay, and gives us sulfonamides, which on alkali, which on reaction with alkali forms water soluble salts. Okay. Next, secondary amines, they react with benzene sulfonyl chloride and forms sulfonamides, but these sulfonamides do not react with alkali and they are ether soluble. Okay, and these both and tertiary amines, they do not react with Hinsberg reagent, therefore they can be easily separated. And among primary and secondary, by separating the aqueous layer, in the aqueous layer we have primary amines, and ether layer we have secondary amines, therefore they can be easily regenerated. In this way the amines are separated. Next, with this I concluded today's session. um, of Amines Part 2 session. In this session, we have discussed about the basic nature of amines, which is a very important topic under amines, and next use of amines as a phase transfer catalyst, and some important reactions, chemical properties of amines, um, alkyl amines, and next separation of amines by using Hinsberg reagent. And in the next session I will discuss about the reactions of aromatic amines and the remaining topics which were included in the BSc syllabus. With this I conclude today's session of part 2 of amines. Thank you.